Hi! On this video, we will take what we have learned about atoms and in particular about electrons and look at how this affects the behavior of an element. So I am going to propose that we make a start on this content now. So we have seen a diagram that looked like this already before. And this was of course the diagrammatic representation of an atom. Let's remind ourselves of the different parts of an atom. So at the very center of an atom, we had the nucleus. A nucleus is made of protons, which carried a positive charge, and neutrons, which were neutral. They had no charge, neither positive or negative. And then we had, of course, electrons circling around the nucleus. And you remember that while this diagram shows these as stationary, in reality electrons are circulating the nucleus at the fast pace, going around it constantly at the same distance. There is another thing that I want to show you here. I want us to be introduced to the fact that typically in what we call as an electrically neutral atom, the number of electrons is the same as the number of protons. This means that the pluses and the minuses are in balance. There are as many of both. So overall, the atom is neutral in terms of its charge. We will come back to this concept a little later, but I really wanted to mention it here at this stage. What we are going to do next is that we are going to look at the number of electrons around the nucleus. And we will take this concept that we are at this stage familiar with and take it a bit further. To make our life a little easier, I have faded away the nucleus of an atom, but it is there. I just don't want us to get distracted by it. So what we are finding is that the electrons are organized around the nucleus in a very particular manner. There is actually more than just one shell. Typically, we are most focused on the outermost shell, but I think that it is going to be very good for us to go through the process of how the shells are filled at least once. And you will notice that I have drawn 3 shells and listed on this table 4 shells. But the number can be greater than this. But this is enough for us to focus now. So let's focus on this first electron shell. And it can contain either 1 or 2 electrons, but never more. 2 is the maximum number of electrons that fit in here. But what do we do then if we have an atom with more electrons than that? We do need to have somewhere to put them. Well, what happens is that we recruit a new shell, and this would be known as our second shell. Notice how the second shell is physically larger, so we can fit in there more than just 2 electrons. In fact, the maximum number of electrons that we can fit on the second shell is 8. So in total, we now have 10 electrons that this atom is holding. But the outermost shell is going to be the most interesting one to us, since it is the shell that determines whether an atom is eager to react with the other atoms when it comes in contact with those. And we can continue the same system of adding more electrons to the subsequent cells. Some find it that the third cell is a little bit confusing one. This is because although it can hold 18 electrons in total, often it actually does not fill up further than 8 electrons there. This is a little bit more of a complicated explanation behind this, but you do not have to worry about it at this level. For those that are interested, I can share that what happens is that after 8 electrons are on the third shell, we start filling fourth shell, and then later on come back to fill in the rest of the electrons on the third shell until it has 18. But as I said, at our level, just think of it as the first shell holds the maximum of 2 electrons. The second shell holds the maximum of 8 electrons, and the third shell holds the maximum of 8 electrons. And we could, if we wanted, continue further, but I think that we will just keep our focus on the 3 first shells. That will give us plenty to think about. So the principle is quite simple. When one shell becomes full, and by this I mean that it has now the maximum number of electrons that it can hold, we move on to the next shell. And really what is most interesting to us usually is the outermost shell. This was because it is the outermost shell that determines the element's behavior, how reactive or non-reactive this atom is going to be. So often you might see diagrams where the only outermost shell has been drawn. And of course, it does not have to be just filling more and more shells. We can also give away electrons and move a shell backwards once the outermost shell has been completely emptied. So you might still be curious about what is the big deal that I make about this outermost shell being so important for the reactivity of an element. We call this shell valence shell. If you think about it, all of the reactions will first take place on the outermost surface, so the outermost shell. Or should we call it really a valence shell, as we just learned? So there must be something that determines whether an atom is very stable or very reactive, or something in between the two. Well, when the outermost electron shell is full, the atom is very happy with its current situation. It is not in a rush to gain or lose any more electrons. You can think of it as being at its happy place and not wanting to change that situation in any way. Atoms are like this, known as stable atoms. They do not really react with other atoms. We can also have a situation where an atom needs to lose a few electrons or gain a few electrons in order to get its outermost shell, the valence shell, full. These atoms are very reactive. The use of earlier analog, these atoms are just a little step away from making it to their happy place, so they are trying hard to get there. So we often find atoms that are in this situation being very likely to react with other atoms. So I have here an example of an atom that only needs one more electron to have its full valence shell. So it is going to be super reactive. And here is another example where this atom will have a full valence shell again, as long as it gets rid of this one electron from its outermost third shell. If that is removed, it has now its second shell as its valence shell. And this shell is full with 8 electrons. Now this atom has become very stable. I hope that this makes sense. And this is where the periodic table of elements becomes super important again. Remember this table, which was organized in a way that just by looking at it, it can tell us if an element is stable or reactive. And that is exactly what we see from there. The group at the very far end on the right containing helium, neon, argon, krypton, and so on. So this group, which I have highlighted on a dark orange, is very stable. These elements have a full valence shell, so they are really not in a rush to go anywhere from their happy place. Then, the very first column instead, we see their elements such as hydrogen, lithium, sodium, potassium, and so on. Here, all these have only one electron on their valence shell, so they are desperate to get rid of it, as then the shell under this would be full. So these elements are very reactive. They are so close to it that they are working super hard to get to their happy place. And we see also another option in the second last column on the right. This column includes fluorine, chlorine, bromine, iodine, and a few others. All these elements share characteristics that they have 7 electrons on their valence shell. So they really need only one more electron and they reach a full valence shell. These elements are too very reactive. They are so close to getting to their happy place that they will work hard to get there, and therefore they are very active in chemical reactions. And of course, rest of the elements that we see in the periodic table of elements fall somewhere in between these two cases. So this is how periodic table of elements works. Does it make more sense now as for why it is laid out the way that it is? So the last concept of this video that I want to talk about before we wrap up this section is all to do with chemical reactions. But before we jump into discussing that in a more detail, let's try to see how this all connects with what we have learned about atoms wanting to always find their happy place, so to speak. So just as we learned, atoms always try to reach a state where their valence shell, remember this was our outermost shell, is full. When they reach that state, they are very stable. So did not really react to other elements that eagerly. They are happy as they are. And if the valence shell was not full, but just very short of that, well then the atoms are more reactive. We see an example of that just here at the bottom of the screen. So we have an atom with only one electron on its outermost valence shell. And this happens to be the third shell. So in order for this situation to either have come about, there must be full second shell underneath with 8 electrons on there. So in order to get full valence shell, the easiest way for this atom to achieve this is to get rid of one electron. Because we really want to do that, if we were that atom, we are going to be really reactive in hopes that our efforts pay off. And when we finally manage to do this, we have now an atom that has a full valence shell. And it is very happy with what it is, where it is at, so it does not really need to try to do anything to change. So this atom on the right is now stable. It is not very reactive at all. So that was when we get rid of one electron. But we can do another thing. We can have a situation like in this example, where we see an atom with 7 electrons on its outermost, so valence shell. And this is in this case the atom's second shell. Well, this atom is now so close of being happy, and by this I mean having a full valence shell of 8 electrons on the second shell, that it is very reactive. It is actively pursuing to fill that missing electron. And when it achieves that, well, then it has managed to reach its happy place. It has a full valence shell and it no longer aims to change things actively. Now it has become stable. So far we have seen those two strategies, either giving away or gaining electrons, in order to achieve the ultimate goal of a full valence shell. There are actually other ways to achieve this, and we will have a look at those in the next video. But for now, we should note that this process of giving away or gaining electrons results in these changes, giving rise to the formation of chemical bonds between atoms. And there are different kinds of these, and we will have a look at those again in the next video. And the processes where electrons are given away or gained are known as chemical reactions. Let's have a look at a definition. So, in a chemical reaction, there is some sort of a change, a physical rearrangement of parts of the atoms that are involved. And when this happens, the atoms involved may form new kind of combinations, giving rise to a new molecule. And I think that this is a good definition, but I think that we can do even a little bit more. What I want to draw our attention to is that in this process of a chemical reaction, original substances are rearranged into new substances. And this is an important concept for us too. So the term that we use when we talk about original substances, or if you wish, what gets into the chemical reaction, is reactants. And what we have now as the new substances, so essentially what comes out of the chemical reaction is products. So let's update our figure below to reflect that. Now this looks more like it. So let's look at these terms and this concept by using an example. I think it's always a good idea to do that. So here I think I have a nice example. We have as our reactants 2 hydrogen atoms and 1 oxygen atom. And as a result of this chemical reaction, we have as product water molecule. So this would be known as a chemical equation that we have shown here. But it does not have to be that fancy and scientific one. We can do much more imaginative. In this example, you go to the school and study there. So you and school and studying are our reactants. And out of this reaction comes a grade and graduation. So the grade and graduation are our products. But these reactions do not always have to be just about building up something from smaller parts. It can also go the other way around. And it often does that we are breaking down molecules. Let's have a look at this. Here we have hydrogen peroxide as the reactant. And out of it comes as products, water and oxygen. This is why you do not leave a bottle of hydrogen peroxide open, because otherwise you will end up soon just by having a bottle of water and some oxygen in the air. If a reaction can go only one way and not backwards, so it is a one-way reaction, then it is known as irreversible. But this is not the only kind of reaction that can take place. Some reactions can also go both ways, back and forth. These are known as reversible. And here is one example. Here, the reactants, bicarbonate ion and hydrogen ion, join together to form a product that is carbonic acid. But this reaction can also go the other way around. Carbonic acid, which is now a reactant that can be broken down into bicarbonate and hydrogen. Or sometimes, some chemical reactions can even include multiple steps. Here we have the previous formula followed by one more step. Now we make as a product carbon dioxide and water. Looks pretty impressive. And as you see, this is a reversible reaction. It can go into any direction. The following, what I say, is not something that I expect you to know. But for those of you who are wondering why this formula looks familiar, it is of course our carbonic acid equation. This is how hydrogen is transported in human blood and eventually eliminated both as a carbon dioxide that we breathe out and as a water in urine. I think that this is an excellent spot for us to stop with this video. I think that we have taken very basics of what we learned in the first video about the parts that make an atom, and now we have in this video build on that. We have seen the importance of electrons and the number of electrons on a valence shell. And we saw that that was the very basis for why chemical reactions take place. In the next video, we will focus largely on the different kinds of bonds that these different atoms form when they bind together, forming a molecule. I look forward to seeing you there.